Welcome. We stand at the precipice of discovery, ready to explore the largest and most complex scientific instrument ever built, the Large Hadron Collider. This machine is not merely a feat of engineering. It is humanity's most ambitious attempt to answer the most fundamental questions about our existence. We are embarking on a journey to the very frontiers of particle physics, seeking to understand the nature of matter, the forces that govern the cosmos, and the story of our universe's origin. The LHC is our window into the first moments after the Big Bang, a powerful tool that allows us to recreate the conditions that shaped everything we see today. Let's begin by appreciating the sheer scale of this colossal endeavor. The sheer scale of the Large Hadron Collider is difficult to comprehend. It is a 27-kilometer subterranean ring that represents the pinnacle of modern engineering. This massive infrastructure is buried 100 meters beneath the Franco-Swiss border near Geneva, a hidden cathedral of science, where the most energetic collisions in human history take place. It is operated by CERN, but the LHC is truly a global collaboration, uniting thousands of scientists from over 100 countries in a shared quest for knowledge. This isn't just a European project. It is a testament to international cooperation, proving that when the world works together, we can build instruments capable of probing the deepest secrets of nature. But how exactly does this colossal ring accelerate particles to such incredible energies? To achieve the necessary energy for discovery, the LHC must accelerate particles to nearly the speed of light, a feat accomplished through a complex system of powerful magnets. Within the 27-kilometer ring, two beams of protons travel in separate, ultra-high vacuum pipes, guided by over 1,000 massive superconducting dipole magnets. These magnets bend the beams around the circular path, pushing the particles to 99.9999999% of the speed of light, a truly relativistic velocity. Precision is paramount. Before the beams collide, special quadrupole magnets squeeze them, maximizing the chance that two protons will smash head-on. These collisions are what we seek, but maintaining these beams requires an environment of almost unimaginable extremes. The operation of the LHC demands conditions that are colder than deep space, a necessity for the powerful magnets to function. To achieve superconductivity, the magnets must be cooled to an astonishing -271.3 degrees Celsius, or just 1.9 Kelvin above absolute zero. This makes the LHC the largest cryogenic system on Earth, utilizing 120 tons of liquid helium to maintain this frigid state. This extreme cold allows electricity to flow through the magnets without any resistance, generating the immense magnetic fields needed to steer the near-light-speed beams we just discussed. Simultaneously, the beam pipes must maintain an ultra-high vacuum, far emptier than the space between planets, ensuring the particles have a clear path to their destiny. These precise, extreme conditions set the stage for the collisions, but we need specialized instruments to capture the aftermath. When the high-energy beams collide, the resulting shower of new particles is captured by giant detectors that function like the world's fastest, most complex cameras. These detectors are massive, multi-layered instruments designed to reconstruct every detail of the collision event. ATLAS and CMS are the general-purpose workhorses, designed to hunt for a wide range of phenomena, including the famous Higgs boson. ATLAS is specialized, focusing on recreating and studying the quark-gluon plasma, the primordial soup of the early universe. Finally, LHCb investigates the subtle differences between matter and antimatter, seeking to solve the mystery of why our universe is made of matter at all. These detectors are where the raw data of the universe is collected, allowing us to move from engineering marvel to profound scientific discovery. The discovery of the Higgs boson in 2012 was a monumental achievement, confirming the final missing piece of our fundamental theory of reality. This particle validates the existence of the Higgs field, an invisible, pervasive energy field that gives fundamental particles their mass. Think of it like wading through treacle. The more a particle interacts with the field, the more mass it acquires. Without this mechanism, all particles would be massless, moving at the speed of light, and atoms could never form. This breakthrough solidified the Standard Model, earning Peter Higgs and François Englert the Nobel Prize. But the LHC's work didn't stop there. We also use it to recreate the universe's fiery beginning. Following the general-purpose detectors, the ALICE experiment takes us on a journey back to the first microseconds of the universe. ALICE achieves this by colliding heavy lead ions instead of protons, generating temperatures a staggering 100,000 times hotter than the sun's core. This extreme heat literally melts the protons and neutrons, dissolving them into their constituent parts. the quark-gluon plasma. Studying this primordial soup allows us to understand the strong nuclear force, the powerful glue that binds matter together. It's a direct window into the state of matter that existed before atoms could even form. But even with this knowledge, a profound imbalance remains in our universe. The LHCb experiment tackles one of the most profound existential questions in physics. Why is the universe made of matter? According to our best theories, the Big Bang should have created perfectly equal amounts of matter and antimatter, which would have instantly annihilated each other, leaving behind only energy. The fact that we exist means there must be a tiny, subtle difference between the two. LHCb meticulously searches for this asymmetry, known as CP violation, in the decay of heavy particles. Finding a sufficient imbalance would finally explain why matter survived the early universe, allowing stars, planets, and us to form. Yet, even with the standard model complete, we know it's fundamentally incomplete. We've confirmed the standard model, but we know it only describes about 5% of the cosmos. The vast majority of the universe is composed of the mysterious, unseen components we call dark matter and dark energy. This is where the search for new physics begins. The LHC is actively hunting for evidence of supersymmetry, or SUSY, a theory that proposes a heavier partner particle for every known particle. If found, these SUSY particles could be the long-sought candidates for dark matter. We are also probing for more exotic phenomena, like evidence of extraspatial dimensions that might only become visible at these colossal energies. We've discussed the search for new physics, but that search generates a colossal amount of data. The LHC is not just a particle accelerator, it's a data factory. Millions of collisions happen every second, creating far more information than we could ever store. We use sophisticated trigger systems to filter out 99.99% of the noise in real time, keeping only the most interesting events. To handle the sheer volume of what remains, we rely on the worldwide LHC computing grid. This global network links 170 computing centers across 42 countries, allowing scientists everywhere to access and analyze the results. This collaborative effort recently hit a staggering milestone: 1 exabyte of stored scientific data. That's 1 billion gigabytes, a testament to the scale of this experiment. But we're not stopping there. We're already planning the next phase of discovery. That massive data processing is necessary because we are constantly pushing the limits of the machine. The journey is far from over, and we are now preparing for the high-luminosity LHC upgrade, or HLLHC. This project is designed to increase the collision rate tenfold, dramatically boosting our discovery potential. More collisions mean we can make far more precise measurements of key particles, especially the Higgs boson. The HLLHC is scheduled to begin operations in the mid-2030s, ensuring the LHC remains the world's premier particle physics facility for another decade. Looking even further ahead, CERN is already studying the Future Circular Collider, a proposed 100-kilometer ring that could take us to even higher energies. This relentless pursuit of knowledge has benefits that extend far beyond the laboratory. The Large Hadron Collider is a powerful symbol of science without borders, demonstrating what humanity can achieve when we collaborate. The technological legacy of CERN is profound. We often forget that the World Wide Web was born here, created to help scientists share data across the globe. Today, CERN technologies underpin life-saving medical advances like MRI and PET scans. Beyond the technology, the LHC inspires the next generation of scientists and engineers to tackle the universe's biggest questions. This quest to understand our origins and the fundamental nature of reality is the ultimate benefit to humanity. We continue to unlock the secrets of the universe, one collision at a time.